but next week isn't going to be so nice.
All right. Hopefully this thing works. So I have a new computer, especially so it doesn't burst into flames.
What is it called?
Oh, actually, this is a bit sneaky of me. The old one became Wombat, and this becomes Platypus. I didn't want to lose Platypus. Seems sad. So that happens sometimes. Like my cell phone is Willy Wagtail, which is a very cute little black and white bird. It's kookaburra and sulfur-crested cockatoo and sooty. No, it's a different kind of owl. That little one there. Yeah. The sooty owl. What is it? Its name's on the bottom. Okay. Yeah. I think that's enough naming. Oh, there is another one. Storage devices get their own kind of taxonomy. So this is the Cooktown orchid. So this is the flower emblem of Queensland, right? So the Tasmanian blue gum is another one I have. So I'm going through storage. So storage is built into the flora, right? Yeah, my big machine is called Uluru, as rock. All right, I'm going to show you a couple of things, and then I'm going to decide what we're going to talk about, because I have two forks here. And all right. Heritage, right. Okay, we talked about river networks earlier on. Here's a piece that just appeared in Science.
To most of us, river networks appear to be fixed features of the landscape. In fact, many rivers define political boundaries that have been in place for centuries. But what if those boundaries are moving? Scientists have long suspected that river networks are not as static as they appear. Some rivers look distorted, and others contain rocks or aquatic organisms that can only have come from other rivers that aren't currently attached. This suggests that rivers have been shifting and moving across the landscape over millions of years, but until now, there has been no way to measure this change. Researchers at MIT and the Swiss Federal Institute of Technology have developed a mapping technique that measures how much a river network is changing and in what direction it may be moving. The technique focuses on a river network's drainage divides, the ridgelines that separate two neighboring river basins. As rainwater flows down either side of the drainage divide and into opposing rivers, it erodes the underlying rock, creating an imbalance in the river network. To reach a balance, the drainage divide must shift to assume a more stable pattern. With this new measuring technique, researchers can determine the direction in which a divide would have to move to bring its river networks into balance. Knowing where river systems are shifting may help scientists understand how these rivers shifted, diverged, and merged over millions of years. This knowledge may help solve some long-standing mysteries in geology and biology, such as why some rocks and fish that seem to belong in one river basin are also found in another.
Anyway, it's pretty cool. We'll see. I'm not sure. I haven't looked at it in depth. It's published in Science, which doesn't mean it's right, but it's an interesting achievement because, right, we have a snapshot of the evolution of our landscapes, and it's in principle kind of hard to back out how that came to be or how it may evolve. So that's the claim here, at least. So they found some places seem to be stable. Somewhere, I think the southeast of the U.S. look like it might be kind of moving around things. So there's a term for this in river networks, which is piracy, right? So just to get a little carried away, but geomorphologists want to make it sound better, right? So that there's piracy, so that parts of catchments might get stolen by basins, so they can shift, and there's sort of a funny connection because we've had all this stuff about the South Pole experiment, confirming that possibly confirming the inflationary universe hypothesis, and so one of the big problems, right, has been that we see these the universe. What we can see that we have these parts that have the same temperature, but they're a long way away, and they seem to be correlated. But it's a strange thing. So in some way, there's a very small little earthbound version of that here, where you have why are these fish the same over here and here? They couldn't have climbed up there unless they were backpacks, which would be a much better scientific outcome. Smoking, getting. So I guess that theory doesn't work. Anyway, but so that's kind of a fun thing. So, all right, okay, good. So I wanted to throw that in, so I'll incorporate that properly. So yeah, whole paper here, well done. Most of these characters are actually at the Swiss place. Okay, what else? Okay, so you guys, I've mentioned, the big story in Parks was there's lots of things, right? Universality, scaling, there were big stories. And one of the questions is how universal is universality? There's a nice piece that's just appeared from Leo Kadanoff, as someone I highlighted at the end of that course as being very famous in this. And so this is a memoir, I think, as far as I can tell. It's obviously evolving, but he's a sort of a superhero, and I mean he is a superhero in physics. Many of his students are incredible people in all sorts of areas now. So yeah, basically 63, 71, we did this great thing. And it's right. So there's scaling, universality, and renormalization, which was a key part of what we talked about. And that's moved out from particle physics into economics and biology. Maybe we can get into literature one day, something like that, which he kind of alludes to, I guess. So what next? This is a while ago. Wow, yeah, it's a long time. So yeah, and then he talks about what he's done since. And so one of his things is to go from place to place, demonstrating his wares to others and getting people inspired. So this is a nice thing to read. He's a very, very famous scientist who helped revolutionize our thinking about the natural world. Okay, just a bit on the archive. This is books. We're trying to understand things. This is a fun thing I want to show you. Okay, some of you guys have seen this, but this is totally exciting. Okay, can I get this to... Yeah, maybe. Wow, that's weird. No. Yep. Okay, so this is a preliminary device, but it's part of our happiness measurement thing. So this is based on tweets from 2013. If you've seen it, but if you haven't, this is fun. Andy Reagan put this together. We have static versions made in MATLAB, which are much more painful, but this is where we want to go. So it's D3, right? Big deal. Nice JavaScript action. So you can click on a place. So this is Hawaii, and this thing here starts to show you why. It's based on words, and we won't go into great detail, but this tries to tell you why Hawaii is happier. It seems happier. It's the happiest one. We're going to have more data here than everything else. Our instrument behaves very much like a kind of a physical one. So there's a lens aspect here. The idea is we're throwing away some words that are neutral. These are very happy words. These are positive words that we're using to assess things. Not to go into the details too much, but there's some really nice features. So for instance, you can, okay, let's get Hawaii. And then you can click on this and you'll just see these are all the positive words that Hawaii uses more than everyone else, right? And there are these negative words that they use less than everyone else. There's a lot of swearing. They use bored less and bad less and hurt and don't and so on. Some swear words. You can go to some fun places like Louisiana. So this is why Louisiana is less happy than Hawaii, right? So it's saying some good words less. Obviously it says Hawaii less, but then there's these blue ones are why these are bad things it's saying more. Obviously this is an unfiltered kind of source, so that's from weather tweets. Weather stations tweet like crazy, so you have to sort them out. Sort of ambulances actually and police, and so you have to kind of deal with them. But pressure and humidity are obviously weather tweets. So we have to deal with that. But really, really a kind of a fun thing. So then you can play around with this guy, and it changes automatically. There's all sorts of things. Okay, now I'm doing bad things. Eek. Yeah. But yeah, the comparison from state to state is fun, right? So we've got North Dakota is not as happy as Utah. And this is, you get some sort of the texture Y, right? So does it make sense? Vermont, killing it. Vermont's interesting. So Vermont actually, one thing we haven't included here is variance, really. So they are saying happier, Vermonters on their tweets, of course, some selection of Vermonters. They're being happier than everyone else for these positive words here. This is sort of the bulk of them, and this is the bulk of positive words that they're using less. These are the bulk of the negative words they're using more. So these things are going against Vermont being happier. These ones are helping, but overall it's a balance in favor of Vermont. And if you click on something like so these are the happy words, right? So there's special and resort. So obviously skiing. Vermont is saying they're special. I'm not sure what that is. There's a lot of less swearing. So I think, and we've seen this before in different views, even with blogs, that Vermont has just a smaller emotional spectrum, actually. It's a little tied down. It's happier, but it's a little tied down. So Utah is very high. They're doing well. But Hawaii is terrific. Yeah, so the ones in pale colors here are bad. But this correlates pretty well with Gallup polls and so on, right? So it's surprisingly good because it's just crazy people on Twitter. Okay.
So what is green showing? Is it like the average?
Yeah, we're going to improve this, but the darker the green, the happier. Yeah, so the paler. So we'll improve that, and we'll have a list that will change here as well, right? So as you change this lens, it's like putting on a green or a yellow or something, like it's a lens that changes the way. So you can do things like this. You can let's block out all the negative words and then just look at, these are just comparing places by their positivity, right? So these are these are all very positive words. I know I'm not really defining this very well. What is that? Oh my God, there's a thing. Okay, someone drew on it. So for instance, Hawaii is thrilled with itself, and of course it's again all those words. Why is it so positive? Oh, it's true that Hawaii has a mixed kind of, it's a mixed place. I mean, there's some poverty there and all sorts of things, but there are tourists, obviously, and you can imagine trying to filter them out because you can see if people tweet in different places. I mean, these are hard things to do, but you could do it. So you could see if it's the tourists versus the locals, how that's working out. It is a nice place. It's always 70 to 80 degrees. I mean, it's not, and the infrastructure is good. The U.S. has put a lot of, it's true, right? So nice tunnels through mountains and things, and then, well, I mean, here's a sense of it. This one, Diamond, actually, that's a reference to Diamond Head National Park, which is a crater, which is a fun thing to run up. If you ever go there, you should run up, and you get to a U.S. on top of all these mountains in Oahu are all these U.S. bases, which is they're insane. I mean, some of them are just. There's one you can get to. You get to it by it's a railway, Cocoa Head. It's a railway. It goes straight up a caldera, and its average incline is 40% and has 50%. That's a fun thing to run up. 50% maxes, yeah, and it actually gets steeper towards the end. And at the top, all these places where they had guns and radar, and all sorts of. There's one place that's incredibly scary to me. I don't like heights, but called the Haiku Stairs. Wow, craziness. All right. All sorts of things. This one is, this is the last 15% of Count of Monte Cristo versus the first 15%, just for fun. And it's in different, so this is in French, so that's sort of the achievement here is to have had French evaluated. We don't have any, I'll show you Moby Dick. I know I'm talking about other things. This is Moby Dick. That's why the last 15% is bad, right? So there are a few you have to throw out. So we need to get rid of cried, and we can do that. And coffin. Coffin is just a last name in Moby Dick, right? Starbuck is there. I mean, these are names of characters. So there are coffins still on Nantucket. So you want to take that one out because it's not what you think it is. And cried are just yelling, So we could take those out. So that's easy to take out. It doesn't change the overall score much, but it'll change its texture. But you see bad things, right? Cowardly, broken, cursed, blind, wrecked, fool, killed, mad, evil, fire, missing. So you might dispute a few of these words, but the texture it kind of ends badly there, right? Which is not true of Count of Monte Cristo because it ends well. Right? Excellence, vie, maison, right? All these good things, right? It's good. We're not in prison anymore suffering, and we have crushed our the evil people. So you can see it ends on an upswing. This is any Russian speakers? We'll add a translator thing, but this is Crime and Punishment. Again, preliminary thing, but the last 15% not so good because it starts off saying I'm going to save the world by killing this old woman, which is nasty, but she's evil. I'm going to make good things out of this. She's a pawnbroker. I'm going to make the world better, and then the punishment is all in here, and it unravels. Fun Russian stories. Very good to dig into. All right, sorry. Always with the preludes. Okay, so which one should we do? I kind of want to talk. What's that? Should we roll a? We should do a. We should flip a coin. Flip a coin. What's that?
Are we moving halfway through?
We have to. Yeah.
Okay.
Yeah.
How
Wherever we can find.
Yeah, with random networks.
We're gonna
or
move just,
generalized.
it's fine, you just follow us.
What's that?
Random networks or generalized contagion.
Generalized contagion, maybe? Should we flip a coin?
What's the other option?
Well, otherwise we do assortativity and then mixed. We're going to do both. We're going to do these anyway.
Oh, we haven't done this sort of thing yet.
No.
So it's
I think generalized contagion, because we'll do this. It's not a network thing. It's not explicitly a network thing. There's some math in this. This is good fun. This is really good fun. But the thinking behind this is very important, and there is still there's a long way to go still, and there have been some real some study which I don't have in here. It's a thing to add. The dosage, the idea of dosage mattering, which sounds a little funny, but it's clearly the biological idea, right? You get sneezed on a few times, and then you can get sick. There's a dosage sense. You get doses of something, but you also get that from whatever it is, marketing or religion or politics. You get doses in a sense. Okay, so we'll try to. What we're going to do is combine biological and social contagion together, right? So let's say we can make a general model. Right? It's going to be very simple, very parsimonious, but from which you could build out. So if you remember, I'll give you a little recap. It was the SIR type model, very famous, been around for a long time. Wrong. We'll make another wrong model, right? But it's for biology. It's inspired by how diseases might spread, and it's used for that. And then the threshold type models, which feel very, they're reasonable things, but again, toy models, but they're very reasonable things. Showing Granovetter, it's famous body of work. But we'll see if we can bridge those things together, because they seem very different. They are very different. One is you get sneezed on, and you have an immune response. The other one is it's social. You remember, you're looking at what your friends do, and you're remembering what your friends do. That seems like a very different thing. So we will manufacture a kind of an umbrella model, and we're not going to put this on networks because it turns out to be super complicated. In what I'm going to show you, we're not going to put on networks yet. That's still kind of an open thing, and as I said, we need more real. I'll see if I can get some real examples together. I know I have some. I just need to force them onto slides. Okay, food is here. All right, people. These guys continue to be crazy people. Okay, so I'm going to frame biological contagion as independent interaction types behavior, and social ones these kind of social ones as interdependent. And then the bulk of the work will be getting into this generalized model, and we'll do a little bit of applied math. We'll have some fun with how this works. And there'll be kind of again, it's looking for universality classes, right? What are the sort of main behaviors? Good, well done. And universality, we love it, right? And so we'll get to some of that, and then we'll of course show how it all kind of goes bananas beyond that. Okay. But this is what we're trying to get at. How many different kinds of contagions are there? I don't want to have as many glossy slides in here, but when people say the Da Vinci Code spread like a virus, are they being crazy? Is that just literary flourish? Is it really like that? I'll add some more examples of studies that have just been done in the last few years. But we'll get to that. So can we categorize it? Given something spread in a certain way, can you say this was a social type, threshold type contagion? Can you see that after the fact? Can you see if it was an independent interaction one? More like this spread more like, did this thing kind of spread like the flu, or right? Did Harry Potter spread like that? Okay. And we're going to think about mean field models, right? So if you remember Granovetter's model, that was explicitly a mean field model. The SIR type models, they're all explicitly mean field originally, which just means random mixing, which is wrong. Okay. All right, so I'm just going to remind you of these things. I can flip through these pretty quickly, I think, but get these same words going again, right? SIR, susceptible, infective / infectious, infected, different ways of, and people will say recovered or removed or refractory, but right, this is the idea. You're prone to getting it, you've got it, and you're out of the game. And you can cycle through these things. Yep. So we're going to make them fractions. Typically, it's S plus I plus I, right? So some unknown population, absurdly an infinite population. And we've tackled this in Parks as well. All right, so as I said, random interactions, sometimes called mass action principle, right? So everyone is bumping into, you can imagine if you want to think of individuals being in this game, then they're bumping into each other, or you could actually really think of them as a mass that's interacting with another mass. So a very important thing is the interactions are independent. There's no memory, which is clearly not a good model for diseases, because usually you would think you'd get immune response, right? So you'd actually get a memory going the other way, which is get a little bit of a dose from this thing. If anything, you actually produce some defense against it. So next time someone sneezes on you, stop it, okay? So we're not going to do that. That's complicated. You can certainly add that into these kind of mass action models. You can add immune responses. You can add exposed. We've talked about that, right? You can be exposed, so you've got it, but you're not actually exhibiting the disease, which very sneaky disease. The best diseases do this, right? You have it, but it doesn't show itself until you've said hello to all your friends. Ebola is a stupid disease, right? It's like, yes. It's like, alien, it's like just wants to get out. It's never going to get off the space station. But it will make it to 3 more films. Anyway, so never preserve things in, which we just did, right? Some maniacs are digging up the Siberia, and it's like, oh, look at this virus. And, hey, it's alive. Wow, that's not going to end well. But this is going on right now. Right? This is yay. Bring back a dinosaur, that's okay. And a woolly mammoth and a Tasmanian tiger, fine. Let's deal with that. We've made movies about that too. But anyway, okay, so you can imagine all sorts of possibilities. This is just a little, I've shown you these things before just to remind you. This is the kind of thing that, this is a discrete time one, it's a serial-autonomous type one. You clock around from state to state. There's a chance you stay susceptible. It depends on how many are infected, right? So it's a nonlinear thing. You have a transition from S to I, and I need to remind you of these because we'll have these in some way after recovery. So there's just a random chance of recovering. There's possibly a random chance of becoming susceptible again. Loss of immunity, that's just a random, so this is a very simple thing. And this goes back to the 20s, Comack and McKendrick, yep, all these good things. So, and here's the differential equation type setup. You've seen these slides before. Here it's very clear, right? So we have the change in susceptibles and the fraction of susceptibles and the infected have these nonlinear terms in them. You can solve these equations sometimes in ways that don't really help. Okay, so this is going to be important again. We've tackled this guy in pox, R0, so this reproduction number. I mean, in simple models, it works fine, right? So the idea is that if this is greater than 1, it's the typical number that one infected person running around with Ebola or an alien inside them gets infected. If you're on a space station and the alien reproduction rate is greater than 1, toast. When I was a kid, I never saw movies, right? Basically, they were just too far away, right? So they filtered to me through books, usually. Like there was a E.T. version. I remember reading about E.T. Like someone would they'd write the book version. It's not and sometimes Mad Magazine would have. I'd get the actual plot from Mad. So I remember Alien was, instead of the alien popping out, it was Kermit the Frog popped out of the captain's stomach. Anyway, so that was my experience of aliens until I think I saw the film about 30 years later. Anyway, I was very confused. Okay, anyway, I understood it was a good film. Okay, so let's see. Okay, so if it's greater than 1, then it takes off, right? It's pretty bad. Bad but fun. Okay. Okay, so this is good. I mean, these are just extra slides in here. You don't have to worry about this. I'm just going to go through this. These are just sitting here. Here's the basic story for this very, very simple kind of model. It's exactly what we had. If you're R0, which is the ratio of beta to R, depending on the model, so beta is the infection rate, R is the recovery rate. So if that's greater than 1, it takes off. Right? And we get a very similar story for networks, right? We get that very similar story for random networks. If we dial up the connectivity, we get a transition to having a giant component. One can think of the network in that case as being the trace. This is a bit difficult, but it's sort of a tracing of a disease that's spread actually, right? So it's sort of an after-the-fact reflection of it. So there's a connection between those two worlds. Nice space transition. Okay, so we like phase transitions. This is something that happens in the real world all the time. We want to see, and this idea of universality, we're interested in generalizing this. So, but this is a typical kind of thing of a disease, right? So you're tuning some feature of the disease. Here it may be, intrinsic to it's the flu. It has some, it maybe genetically changes or whatever it is, or people start, shaking hands more, whatever they do, right? Something is changing the mechanics of this spreading that could shift it from here to here. And that's the badness, right? And so if you're out here, you want to somehow manufacture a way of getting back here. This is sort of just the general kind of big picture of it. But it's this kind of transition. So it's continuous and it's not sharp. It's not sharp, right? So discontinuous is bad because that means, you're going along, it's like, oh, no one's sick. And then something changes just a little bit about the disease, and then suddenly half the people are got carts and bring out your dead, right? And that's bad. You want to go to like 1 cart with bring out your dead, to 2, 3, 8, 16. You don't want to go to like 5,000 carts straight away. That's hard for societies to adapt to. Okay, all right, so I've showed you these things before. Okay, little recap of a recap. So this is Granovetter's model, which reduced it back to, there's no refractory in this, it's just S and I. Okay, so we'll deal with those as well. So you're either susceptible or infected, you drop back to being susceptible but possible. So you remember this story, so people have threshold responses. This is a very different kind of setting. There's some distribution of thresholds. If we integrate this function, we get this, it's CDF, and we argue that that is in fact the map that shows you how this system will evolve. This is a mass action kind of story again, right? Everyone's watching everyone else, or or at least randomly. You can think equivalently that. Well, this will help us go to the more general model. So you could watch everyone else through a media kind of thing, right? Here's what everyone else is voting for, or it could be that you're sampling people repeatedly, right? And kind of a lot. So at the end of the day, you've sampled 100 people's views, so you get a proxy for what the whole average is. And we looked at all this stuff when you go to a network, how things change very different. You're very, very different. If you've got a fixed local network, you have very different kinds of patterns. We'll go back to networks later on, but we're going to pass through this little test first. Okay, so this is a critical mass kind of model. Right, so if the initial condition is below this fixed point here, then it dies out. You've convinced all these people to read Twilight, and then they're like, it's okay. But if you started with, more people up here, then they get to these ones who really hate it, who need 99% of their friends to like Twilight, and then they're like, okay, I'll read it. But and then it takes off, and the world goes to hell. So this is an interdependent. What I'll call an interdependent interaction model. It matters, it matters what that one does, and that one does, and that one does, and that one does, as regards your possibility of infection. So the disease one, you bump into someone, you get it or not, and then you forget about it, right? Which is weird if you don't get it. Okay, so all right, so that's a recap. Do we need to say anything more about those guys? Then we're going to try and smush them together. It's a Smoosh-in. Boston? No? Anyone? Ice cream? They have Smoosh-ins. Okay, so Boston is kind of the ice cream capital of the US. This is just a detour for you to know. It really is. This is where you go, if you're starting an ice cream thing, this is where you go and get it tested out. Yeah, sure. There are all these little local places there. Christina's in Union Square, very nice. Ben and Jerry's, that's where they went. They had to go and test it out. I mean, they're mad people, but they eat ice cream in the middle of the winter, right? And they really like it, and they'll wind up. And one of the Smoosh-in is when you ask for a bunch of whatever it is, and then you get to put in your ice cream and put it in. Smoosh-in. Okay. So we're going to make a Smoosh-in experiment model. Okay, so independence of infectious, these are the simple ones, right? This is the simple ones, right? All about simple models. Okay. So you can think of it as sort of like nailing ideas to math a little bit. That's what we're doing, right? We're trying to sort of, we're not going to explain all of the world, but we're going to get some good ideas. Okay, the threshold models are just proportions. So that's a very different business. It doesn't matter what the sequence has been. Right? You also, in principle, the system has a memory. So if 28 people were on, they'll still be on. in the Granovetter model. So that's so that's true. So it kind of has a memory. You don't have to do. There's no burden on the individual. There are a lot of very odd things hidden in random models. When there's randomness, you think you're getting something, but cool. But it may be that randomness is really burdensome on the individual in your model. So you have to think about that. All right. Okay. This is also true. There's this notion of immediate polling, right? So in threshold models, so you have 38 friends, and then every time step you go, whoop, you're on Facebook, and all the time you're like, what are they all doing? What are they all doing? Right? So you're kind of everyone's a psycho stalker of their friends. So maybe we can assume that. That's okay, all right, for teenage people. All right, so of course the mean field models, there's nothing about networks or context or any of those things. So, and then networks, of course, are just part of it. As I said, these things these mean field models capture kind of media type things, right? Because it's like you're getting this big signal from the outside world. All sorts of other things are happening as well. Of course, I mean, this is coming through all sorts of channels now, right? It used to be just TV and maybe newspapers, and now it's just all sorts of things. Okay, so all right, let's build a fun model. Okay, so this is a lot of goodness in here. Okay, but what is a pretty simple model? So we're going to put memory in. That's going to be a big deal. We're going to put memory in. Yes, humans. All right. And there's some evidence that this might work for some disease type ones as well, right? So there's memory in the sense as we talked about that you have an immune response. So you remember that interaction, but it may be that you accumulate things as well. And I think cholera might be an example of that, actually. So certainly it can happen biologically. So for a clear example, that's not a disease, but allergies, for example, like bee stings, right? So you can build up, you get stung by bees, a little bee comes and stings you every day, or one of its compatriots, right? So that you build up a dosage in your body, and then it can be bad, right? So you have a memory. You have a memory that makes you more susceptible later on instead of being stronger or more resilient. So they can go the wrong way. Yeah. Right. So it's going to possibly make more sense for social contagion, but I'm arguing that some disease type things can work like this. So simply, we're going to have a memory. So we'll have our SI and R, sort of business. We'll have our N individuals. And we're going to stick with our random interaction model because we have to do that first before we put on a network. And same kind of labeling as we've had before. So phi of t is going to be the fraction of individuals that are infected at time t. And so if you're randomly bumping into others, that becomes your probability of bumping into someone who's infected. Right? Why you do it, I don't know. But we're going to have then two pieces. And then so we kind of had beta before. Let's just make it a p here. So this is going to be the probability that you get an exposure, right? Which will be some kind of dose. That doesn't mean you're infected. It just means in that interaction you get some dosage, right? Yeah. And it could be that whatever it is, whatever the thing is, is it spreading? Whether it's Justin Bieber is cool or cricket is awesome, whatever it is, right? Except England won. That's disappointing. So let's see. So if you're exposed, right, you get a dose of size D. So there are these three steps. You bump into people. If someone's infected, there's a probability that they exchange some possible goodness or badness, whatever this thing is that's spreading. And then they get some dose. And we'll make that dose distribution general, right? So there aren't super special people or anything. There's some characteristic threshold. Distribution of doses. And if that doesn't happen, they get 0, right? So they have this little memory string. Okay, so this is how they become infected. So you remember, you keep in your, so you can imagine some sort of memory that decays, right? So 10 time steps ago, it kind of decays. But clearly this is something, it's odd how this works, right? So you'll remember, in the last week, you'll remember a lot, if something's talked about a lot, you'll have it in your head, but now and then you'll hear something, it's like, oh yeah, I heard about that last year. And that can matter, right? It's a very peculiar thing. So there's I'll just mention, for this work, I need to have the graphics, but there's nice work now on Facebook, for example, that and I'm sure I've said it, but looks at adoption of Facebook itself. And it's because Facebook and the NSA all know everything about you. They know who your friends are who are already on it. So there's some characterization of that. So this is work by Uganda, John Kleinberg, and others from Cornell, and some of the Facebook team. I think Cameron Marlowe. So it turns out that having a more diverse set of people who are already on it makes that more likely that you'll adopt. So this is, it's not really a memory thing, but it's about the different kinds of doses, right? In doses from different places. So doses in time can have this kind of effect too, like if it comes from a different source and so on, it should add in a different way. But here we're just saying, okay, it's just a dose, right? Just a dose. But you will, in this setting, people are going to remember the last T contacts. So we're at some time T. So you go back in time, minus T plus 1. So you go back in time, and you add up T, T minus 1, T minus 2, back to here. You add up all those doses that you received, some of which may be 0. They could all be 0. Add them up, and that's your current dose in your head or your body, right? And so that is, and so you become infected. You do have some. So this is where we connect back to Granovetter. You have some threshold, and that's when that sum of those doses you have, of some whatever this T is, that's some parameter of the model. This capital T, you become infected, right? And so this is the way we're going to bridge these two things. There's a threshold type thing, and there's a memory story. But you're not looking at everyone at the same time. And so we're not on a network anymore anyway. But you're not looking at everyone at the same time. You're polling people one at a time. So it's cognitively more reasonable, perhaps, for humans. And we had this dose threshold, this dose distribution being whatever it is. It could have all sorts of shapes to it. So your threshold is also drawn from some distribution, just as we've had before. We'll call that distribution G, and that's fixed at time t equals 0. So people have some characteristic threshold for themselves. Okay, so that's S to I. I to R is, so does that make sense? I'll have a little picture. So, nothing too super complicated.
Sort of like a video game thing. You don't get hit long enough, like in Halo, you run around for a while and you just heal automatically.
Oh, yeah, if you've got regenerative. Yeah, you can get right up to the limit. Yeah.
You just have to hide.
That's right. Does that happen in Minecraft? I think it does. It's important. It's not an endorsable product. Okay, so like Halo. Okay, we're playing Halo now. Now, if your threshold has been exceeded, then as soon as it goes below it, so as long as your dose is above the threshold, you're not going to recover, right? So if you're in. But as soon as it drops below, which leads to all sorts of funny dynamics, then you have a chance of recovering. And it goes back to that same probabilistic random recovery rate. So you get an exponential distribution for the time of recovery. Okay. And then if you're in the recovered state, you can become susceptible again, and we'll have this probably wrong. We'll have that same story. But at any point, So if you're in recovered or refractory, should be, then you can't become infected. But SIS again is something we can look at, right? This state is a complication we can get to, but yeah. Okay, so here's a very clear schematic. So what can happen, right? So you're running around, you bump into someone, and they are not infected, right? So then you get no dose. They could be infected. You run it, you contact them properly. It's probably 1 minus p. You actually receive nothing. Probably p. You get some dose selected from this distribution, f. Right? That's the mechanics of an individual's behavior at each turn. So you have some memory, your little ticker tape. Doesn't look like a Halo game, but imagine this is, shotgun. Halo. Like Halo. Just like Halo. Right, so the second lecture we're just going to play Halo. Okay, so test this. Now, we had this SIR model before, right? We had this little guy that I showed you at the start. You've seen it before, but now it's a little more complicated, right? So you stay insusceptible if your dose load is less than your threshold. You just stay there. And with probably 1, you go to infected if your dose load exceeds your threshold, right? So you're always adding up these last 2 time steps. It's possible if in 1 time step, it's just the way we set this up, I guess. So this thing you can relax back here. So with probably R there's a recovery, and rho you go straight back to being susceptible. That's only when your threshold, your dose load is dropped below your threshold, and you stay infected as long as your dose load exceeds your threshold. And then there's this recovery probability. So 1 minus R is you don't actually recover. So that's an extra little trick, right? So that your dose has gone down, but you're not getting better. You haven't gotten better yet. Right? Your dose load's gotten better. You can recover, but not become susceptible again, and that puts you into this state, in which you stay in with this probably 1 minus rho, and then eventually pop back up here. So if rho is equal to 1, then this whole branch disappears. That's kind of why this was done this way. All of this disappears, and you just go back to this state. So that's an SIS model. And so that turns out to be an interesting enough one to study. So what do you think? Can we do it? So that should be easy to study, right? So it turns out that just making R less than 1 is just hideous, right? So, okay, so we'll sort of work up to some things we can understand. So first thing we're going to do is put R equals 1 equals rho. So as soon as your dose load drops below your threshold, you become susceptible again. You recover immediately. So you recover immediately, and you go back to this state, right? So boom. So we've just got, so this is all gone. This piece is gone, and right? If you're above your dose load is above your threshold, you're sick. So that turns out to be interesting. So we'll do SIS and see if this thing can cycle. Stay in certain states. All right, we're looking for fixed points of the system. And what we're going to dial the infectiousness. Right? We have this very simple kind of interaction thing, which we can't really play with. In the past, we've played with networks, of course. But when you're looking at the mass action ones, you're just changing the disease or whatever it is. Right? Random interaction, that's fixed. All right, so we'll look at a homogeneous version first. Everyone has the same threshold, and all dose sizes are equal. We'll just make them d equals 1, right? Because you might as well just normalize it to something. So okay. So everyone's going to have the same threshold, and every time, if you get a positive dose, so P is going to be this parameter. We're going to tune P. We're going to go from P equals 0 to 1, right? So when it's 0, nothing spreads. When it's 1, every interaction with a sick person gives you a dose, and that dose was always 1. So it's very simple. Chocolate? Hit me? It looked like that's what that looks like.
I just have a question about the homogeneous version.
Yep.
All individuals have the same threshold?
Mm-hmm.
That seems...
Well, so we did that with the network one too, right? So we did that with Watt's model. Everyone had a threshold. There's a couple of examples where it was 0.18. Everyone had the same threshold. That meant that if you had 1, 2, 3, 4, 5 friends, you were vulnerable. And so that proved to be a very interesting.
Yeah, I guess I'm trying to think, it's the threshold against the probability of getting sick, or it's the...
So the threshold here is it's the dose load that you need before you become infected, right? So
dose load you need. Okay.
let's get it again. This thing. So you sum up all of your doses, depending on what your time window is, right? So you might remember only your last 1 time step, or your last 10 or 13, whatever it is. You just have some times, which we'll actually keep that the same for everyone. And there are parameters you can go everywhere. We'll vary it, but everyone will have the same memory. Okay, that's another piece. Well, let's say you remember the last three, you add them up, and now it's just going to be adding up zeros and ones. Your dose can either be 0 or 1, so you're going to be adding up zeros and ones. And if that exceeds your threshold, you're sick, or equals or exceeds, you're infected. What do you think?
Yeah.
Vague,
I just
vague,
wanted
no?
to clarify what.
Okay. All right, so this is a homogeneous one. So we'll build out. We'll build out. This is fine. We're going to go through a sequence of models. Yeah.
So I was just chewing while you were saying that.
Mm-hmm.
So if you are just past the threshold to get infected, but then your dosage, how does it decrease? Does it do it?
So you're still interacting with people. It's not a very nice place because if you're sick, you're just like, hey. So you interact with people, and if you're sick, right? So you might get them sick. But if you then go and interact randomly with people who aren't sick, then you're going to get a bunch of zeros. So your little ticker tape, which is your history, is going to start getting zeros in it. And so your dose, because you're remembering some...
Oh, X number of doses,
Yeah. So imagine you have your whole history here.
Yeah.
And then eventually, and you just window it. So as you run your window along it...
So is it possible for you to bounce on right around your threshold every time period?
Mm-hmm.
So you could become infected and just below threshold, and then just above threshold, and just below.
Yeah. I will vote Republican. I will vote Conservative. They're the ones that you want to have a talk to, right? The ones that are stuck. No one's interested in it. Yeah. Yeah. So a ridiculous model for the reason you point out, but it's possible. So, but it's clearly we're adding the ingredient that we need to put in, right? We're adding one ingredient that needs to be put in memory. Memory needs to be put in. Okay, so our lesson one means probabilities probabilistic. So this is just a few settings here. Okay, so it's probabilistic lesson one. D star equals 1. So your threshold is 1. So if you just interact with one person, they give you a dose of 1, you're infected. But you only remember your last time step. So here's an example where the memory is not working yet, right? So let's get this one to function. So they're basically forgetting everything from the past. They forget past interactions. So they remain sick with this probability. And so it just means that one hit, they're in, right? So because we're going to have D, the dose size is 1 for a while. So we can write this down, right? So this is not too bad. So you can think about what's the fraction that will be infected at time t plus 1? Well, it's the, okay, so we've got A, B, and C. So there's a fraction of people who will, so you think of the people, this is the probability that someone bumps into someone who's infected. This is the probability they get a dose from them. They always get a dose of size 1. So this is the fraction that will be infected in the next time step just from interactions. There's going to be some fraction who were infected and, let's see. Yeah, there's 2 pieces. Right, so these are the ones who were infected at time step t. They weren't infected in this next time round, which is this probability, right? So they didn't get reinfected. Okay, so they have a chance to recover. They got a 0 actually, right? So they got a 0 in their interaction, but they didn't recover, the 1 minus r. So we can actually, so we're going to look for fixed points. So this is a nice little thing, right? There's a 1 minus r here, and there's a p, so they're the 2 parameters. But we'll put phi star here, phi star here, phi star here, and phi star here, and unwrap it. And we have a quadratic. So we can do that. Yeah?
I was being excited.
Awesomeness? Okay, right. Okay, so we just said we do that. We'll set phi t to phi star. And we can unwrap some things, right? If phi star equals 0, that works too, right? So that's a fixed point. Okay, so we have to be careful with that one. So in fact, if we cancel that guy off, we've got 1 equals p. So it's a simple quadratic. 1 equals p, right? We're canceling these guys off. That cancels, blah, 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 blah. Good. And we just need to isolate our phi star, so we're going to put 1 minus p, we're going to put that guy over there, we'll divide by 1 minus r, and then we'll put that on this side, so we have 1 minus p over 1 minus r, and we'll put a phi star over there, and we'll divide by p. So that will, and the p gets divided through. It became p minus 1 divided by p, so it's 1 minus r over p. Voila. Yeah, okay, good. Okay, cool. So we get these two guys, right? So this is R is a thing we're going to tune, and P is what's this? I'll plot it on the next thing. So what's that function look like? So here's phi star, which could be at most 1. P can be at most 1. So we're interested in these kinds of diagrams. What's this thing look like?
Whatever R is,
You can asymptote. So what happens when p equals 1? What do we get? Okay, so it goes through here.
and wherever R is,
Yeah, independent of R. What's it look like when p equals 0? What is it?
R is going to go really big all the time.
R is fixed. R is a
It's
parameter.
fixed, but I'm saying the fraction.
They explode, right? Yeah. So, and so in fact it becomes negative, right? So it's this kind of business.
Yeah.
Hyperbole.
Mhm.
So where does it cross? Where does it cross here? We'll call this PC. That's the critical probability. That's a right. So this is what we've done is we've retrieved this kind of basic disease spreading type model.
well, isn't that R over P? Right, if phi star is going to equal 0, then the numerator has to equal 0.
Yep.
Yeah, so that's,
So R P equals R, yeah, R equals, yep, R equals P.
Yeah.
This blob equals 0, R equals, right, so this is PC, we'll call PC is equal to R. Good. So this is consistent with the whole reproduction rate story, right? So when these two things balance, probability of infection balances the recovery rate. That's just at the cusp of where the thing is taking off. When probability of infection is bigger than the recovery rate, it gains, and when recovery rate is faster, it never takes off. So I have these words, but this is a transcritical bifurcation because we had two solutions, right? We had phi star equals 0 as a solution. Wow, look at the happiness. Chaos geeks. All right.
basically.
Dynamical systems geeks. But that's what it is. Mathematically, it's a transcritical bifurcation, right? Because you've got these two solutions pass through each other, and they change in stability. Right? So this is a stable one here. This is a stable one here. So the kind of thing that's happening is if your initial condition was here, it goes whoop to this. If your initial condition is here, for whatever reason, then it would go to here. If it was out here, it goes like this. Right? So we're fixing P. We have some initial fraction infected, and then there's some evolution. So if you're in here, and so it's a classic phase transition. Right? So, and we got it with a zero memory situation. So that feels good. Feels good. Transcritical. Okay, all right. Okay, good. So spreading takes off. I mean, I know it's all on this thing. So, continuous. It's a la the SIR model. Very nice. Cool. And we get that kind of reproduction number story, right? Which, in the way we phrased it, beta over gamma, infection probability, recovery probability, same kind of feel. That's good. More excitement?
Just talking about other
Just
bifurcations.
enjoying it? Okay. Just soaking it in. We'll have some others. Okay. All Okay, that was a really simple version of it. So let's move out to R equals 1. So we're being very careful because it's hard. D star equals 1. So now they recover immediately. They, again, also need just a dose size of 1. But now they have more of a memory. So you can remember, and we'll just say t is greater than 1. So it doesn't really actually matter if it's 2 or 3 or 4. But now there's this possibility of, it could be just sitting in your little ticker tape and that's sliding back in time. But if it's 10 and you get a dose now, then there's going to be 10 time steps where you're infected for sure.
I know that we have to be careful, like, as we increment the parameters T and R, but just as out of curiosity, is there some kind of, let's call it like days maybe, like some actual number that psychologists or behavioral economists have been able to identify for memory of social contagion maybe? Like a realistic...
Yeah, that's really complicated. I don't know. I mean, because people remember things in funny ways, right? I mean, you can remember something from a long time ago very clearly. I mean, there's really interesting stuff about how the fidelity and the time resolution that you have as well. So it seems to be, for instance, when something goes horribly wrong and it's happening quickly, that you're sort of writing it down in your head quicker. So when you go back to remember it, it seems like it took longer. Yeah, because you're sort of actually going back to sort of some event-driven record of it, right? You've sort of put it on a film, and this happened, and this happened, and this happened, and this happened, and you kind of so time seems dilated. So it's just that you kind of wrote more down. I mean, there is an extraordinary. I mean, the extraordinary thing about our brains is that there are some people, right, who've had something essentially go wrong with their brains. They can remember essentially everything that ever happened to them. And there's a Radiolab one on limits, which I advise you to listen to.
The stress one talks about how when you're under these really stressful situations, you remember so much more.
You remember more? Yeah.
Details of everything that happened.
Yeah, your brain gets, it dials up its ability to remember or not, it seems, involuntarily. But there are some people who have remembered essentially everything, and they're often synesthetes. They add all sorts of colors and sparkles and exploding things to whatever's going on. Famous one is this Russian guy, I mean, I believe this is really a true story, who used to give shows where he'd have, a packed crowd and spend 10 minutes fielding random statements from people and then be able to repeat the whole thing. He apparently read Dante's Inferno in Italian, which he didn't understand, but could actually verbatim repeat it all, including what happened in the cafe at the time when he read that little, that sentence. But he eventually crumbled kind of underneath it all because he wasn't sorting things out. Memory is really important for making meaning, right? As you understand the world, you have to forget things, and just for psychological health.
Yeah. No, I think
it's good to forget.
It's going to be really interesting. I just was wondering if there's an actual numerical value attached.
I don't think so. I think it's dialable. I think some things are more salient to us depending on our experiences and so on. I mean, of course, advertisers are always trying to make things salient. I mean, so educators are too, right? I mean, so they're trying to get it locked into your head or to attach to something that's already there. I mean, religions do the same thing too. They're trying to, get a story inside, for good, and bad. Okay, so let's try this guy. We're in simple model world. Okay. I'll give you another bifurcation. Maybe that will make you feel happy. Okay, recovery is immediate. We remember at least 2 interactions, and we just need one of those interactions because doses are all the same size. They're all size 1. We just need one of those to have been a positive interaction. If someone infects you, it doesn't matter what anyone else does, right? So there's an independence thing in there as well. Okay, so we're going to have the steady state again. And so simple kind of thing. You often do this sort of thing. So the probability that someone's infected is 1 minus probability that they're uninfected. And so if it's a steady state, right, so it's reached some steady state, so the probability that you got an infection at any time, or at any time, is phi star for bumping into someone who's infected, and then p for getting the little story about Justin Bieber. Okay. So what's another good? Okay, so 1 minus p phi star to the power of t is the probability that all of those interactions fail, right? That you didn't get infected. So if you didn't get infected in any of them, and then you subtract, that's that probably 1 minus that probably means you got infected in at least one of them. Okay. Right. So at least one of them got you. So that we can write down. All right, and we can solve that little thing. Play around with it. Well, not exactly, but okay. So we have a closed form expression. So you see, the first one we can actually isolate phi star and write down the equation. We're all with ourselves. Adding this minor complication, suddenly we can't unpack it. Obviously, we can solve it. We can use that evil guy's thing to map it or whatever. What's his name? Did something with cellular automatas. I don't know. Irrelevant person in history. Anyway, or we could use, something good like MATLAB or Python. Let's see. So something free and open. So you can plot it. You can play around with this, right? But we can also, we can do a little analysis to see when there's a critical, when phi star just jumps above 0. Right? Okay. So we'll let phi star go to 0. Right, so this becomes small. So 1 minus a small thing to the power of t. We love that approximation. 1 plus tiny thing. No, it's another one. So t is fixed. I know, I lured you in. Right? 1 plus x to the n. For small n. Right?
Small x or small?
Small x, sorry.
Oh.
And this is fixed.
It's approximately 1.
It's approximately 1, but it's approximately fixed. It's the first. Right? Plus order of x squared. Evil?
No, we did this in evolutionary computation for
Yeah, you just yeah. As a tattoo of it. Yeah. So in your head, it's behind your eyeballs, right? Okay, so we can do that. So if we do that, we just get it's 1 minus pt phi star, 1 minus 1 minus p phi, right? So the ones cancel. So we just get pt phi star. So that's good. So we get this actually. Pc is 1 over t. Right, r equals 1 in this, so we're not quite connecting to our previous one, but pc is 1 over t. Interesting. If you do plot it again, it's a continuous phase transition. It has this kind of feel to it.
Sorry, why did we let phi star go to 0?
Because we're trying to find this point. We're interested in this behavior. Right. We can also look at the slope there. We can see that it's greater than 1. We can see when phi star goes to when I guess that's not true. I was thinking about phi star going to so when p goes to 1, 1 minus 1 is 0, so so that's a solution there, right? So it ends up here as well.
Okay.
So that's good. So we've got those 2 points. We can actually solve for p, so you can actually get the whole function out. Sometimes this is wrong, right? So we can plot it this way. P is a function. So we can actually do the right thing. All right, but so instead of pc equals r, it's 1 over t. So we kind of want to reconcile that a bit later on. Yeah, so I'll sort of say something. Right, so PC, what's the expected number of hits when PC equals 1 over, well, just for P in general? What's the expected number of, small p, what's the expected number of hits in your memory of T time steps, capital T time steps that will be on? So when P is very small, it's roughly P times T, right? You have T chances. This is the expected number. So what we've kind of got here now is PC equals 1 over T. So it's kind of right. So 1 over T times T, so it means that we're on that. It's exactly the kind of thing. You can justify from that point of view, right? So PC over T, PC times T is equal to 1. This critical as we deduced from this equation, right? So that's kind of right. The expected number of hits that you're getting when probability is 1/t is 1, right? You're getting at least 1, and that's all you need. Okay, so that's one way to think about that. Okay, so gets more complicated when you try to expand things a little. We're going to keep the dose, the threshold still at 1. All right, so you still just need 1 hit. And then we'll try to let the recovery rate go less than 1, and then we'll have t greater than or equal to 1 in general. Right. So we have this case. This is what we just did. This is r equals 1. Right. So you recover, you go straight back. So if r is less than 1, we have to think about this a little more. Right. So we get the let's talk about this properly. So we get the ones who didn't receive, they didn't receive any infections in the last t time steps because they have to have no infections, right? Because here, if you just have 1 infection in your last t time steps, then you're sick, right? Everyone's threshold is just 1. Okay. And they didn't recover from their previous infection. So you've had a clean, your contacts have been 0, 0, 0, 0, 0. So that's all good. You're not getting infected, but you haven't been able to recover. And you have to keep getting zeros, right? You have to keep getting zeros. So, kind of a funny thing. All right, so you have to think about the dose history. So this is what you had in the past. So here's one history that you might have had, right? So you've got these doses way back in time. You had a 1 here, which you're infected from, and now you've had t zeros in a row. So now you have a chance to be uninfected. All right. So the chance that you're still infected is just 1 minus r, because you finally got to a chance where you could recover by yourself. You fail to recover. So if you've got so you have to count up how many ways there are of getting this thing, and then multiply by this. And then you have to think about all possible history. So it has to be something like this. You have to have a clean interaction history for the last t time steps. It's the only way you can, like it's getting out of your system. Right? You're not hanging around with those people anymore. But that could have gone on. You could have had m zeros after that. Right? And if you've had these m zeros, you haven't recovered for any of in any of these cases. So the probability that so we're going to look at this. That first history I showed you looks like this, history of 1. The probability of that one is, well, you were infected, you had all of these non-infections, you had t in a row that were non-infections, and then you didn't recover. And this one we're calling HM1, m plus 1. Well, so you were infected because of this hit back at t plus m plus 1 time steps ago. You've had zeros. You've had this really nice run where you've no zero. All of these interactions have caused, maybe you've either bumped into people that aren't infected, or you've bumped into people who are infected and then not got a hit. So good. But on the other hand, you've managed to fail to recover m plus 1 times. All right, so this should match up when m equals 0, so we get this. These guys match up. This collapses back to this one, right? It's H1. Yeah. Cool beans. Cool beans. It's a pretty great model. Okay, so but there are more surprises after that. They're really good surprises to come.
Are there more bifurcation diagrams?
Yeah.
Oh, okay.
Jersey.
It's like chocolate.
Jersey. Hey, you can't anything wrong.
Stereotype.
Leave the gun. Take the bifurcation diagram. Bring the map of the interval. All right. Bring the gun too. All right. So, okay. Let's see. So we're going to have to do something kind of crazy here. So the probability of the recovery is probably we saw no doses for at least t time steps, and we recovered. Pretty nuts. Okay. So R is your recovery probability, the probability that we didn't recover for t plus m, and that can go on for m equals 0 to infinity, right? So we didn't recover after t plus m. So we can write these things down. I just showed you those equations, right? So we have this R here for recovery, and then these guys are all about having, this nice string of zeros and not recover. And so geometric sum, right? So we have this guy can come out, this part can come out, but we have 1 minus p phi star to the m, 1 minus r to the m. So that's our, this blob times this blob is our, what do we call it?
Common ratio.
There we go, common ratio.
That
What?
m is
What?
m plus 1
For that guy,
in the next one.
why is there not an m plus 1? Because this is h of m plus 1. So the m plus 1 matches there. Now I'm worried about what I did here. H of t plus m. And it went from m equals 0 to infinity. It feels like that should be cleaned up. This can't be wrong. Craziness.
Yeah, try to map those.
Okay, I'll check it. Damn it. H of
Could
t
be right.
plus.
Could be right.
No, good spotting. Yeah. Is it right? It's well published, but it's okay. So let's see. So there's been a shift, right? This is true. It's got because it was m equals. This is what? No, this is m. Okay. M is here, right? Yeah. So it's 0, t plus m plus 1. M is going from 0, right, this is m equals 0. Yes, it's true. So I think that should, sorry, m plus 1, t plus 1. No, okay, so this last one turned into an R. That's the idea, right? So it was 1 minus, so this, you didn't recover, but
Okay.
yeah. So it's
Yep.
the switch.
Nope. That's
It
right.
was 1 minus out of the m plus 1 because
Yeah,
we wanted
yeah.
to continue the story. But
One of those.
yeah. So the last one is recovered.
Okay.
Put the gun back in the car. Okay, so we don't need it. Found killed by a map of the interval. Okay, so to the p phi blah blah blah. So these are just prefactors. That 1 minus p phi star to the t, and then we have this blob times blob. So it's 1 over 1 minus that common ratio. Okay. And so it's this 1 minus p phi star, 1 minus r, and so we're good. So this is actually a fixed point equation, right? So it expanded very nicely. So when r equals 1, this disappears. This goes to r equals 1, and we collapse back to our previous one. This is very enjoyable. It's very enjoyable. Maybe not for you, but it's a very enjoyable result. So here it is again. So you can do all sorts of, you can play around with this again. We can do the same thing where we look at what happens when we get to phi star equals, this is phi star. When phi star is close to 0, we can see how that behaves to find what PC is. So let phi star become small. So we'll get that 1 minus pt phi star on the top. There, this guy is small, but this isn't necessarily. We could work through it. And you will get, does this make sense? Yeah, you will get this result when you unwrap all of this. The p is tending to 1 over t plus 1 over r minus 1. And we're going to call this 1 over r minus 1 tau. So 1 over r, because it's an exponential decay, r is the probability of failure. So if you think about how that thing behaves, then 1 over r is the typical time scale. It's the mean of this. So 1 over r minus 1 is the mean recovery time, right? It's a simple relaxation thing, exponential decay. So we get these two. So it's very nice, right? We had one of it when r was equal to 1. This disappears. That's what the previous result. So we had the critical probability is 1 over t. But now we get this expansion, right? So it actually means when the recovery rate, it pushes it this way, it pushes the curve this way, because people are staying sick longer. So once you get them in the game, it's easier, so this should kind of feels right. Then it moves this whole curve this way. So it's nasty. If they can recover faster, then that helps the system. But given that you want it to be we're thinking of it as a bad thing. If it's a good thing, then this is okay. This is where they're probably watching HBO again, and HBO would want R to be large. Okay, so yeah, so as R goes towards 1, this goes towards 0, then this thing explodes and PC goes closer and closer to 0. So that makes sense. But it's nice that we've inched away from this. The other one, though, we had at the start was PC equals R. So we get that back too. When we put T equals 1 here, these guys cancel and we get our R popping up again. So that's good. So now we've got all those together. It took a little thinking to move out to this more complicated one, and we'll keep going with that. But here's I've sketched some of these here, but here's a typical kind of thing. So there's actually an example, T equals 2, so you just remember 2 things. You have half a chance of recovery, and if you put that into, so it's 2 minus 1, so it's going to be 2 plus 2 minus 1, so it's a third. So that's right. So this is simulations and the model, so you get 1/3 there, right? So stable, transcritical. So the average memory in the system is 3, right? So there's actually, because of the recovery rate, you've got this real memory of 2. You remember 2 time steps, but you get this extra 1 from having this recovery mechanism, or this chance of staying infected. Good? Okay, well, I think we've really dealt with that. So these dose 1, if your threshold is 1 and the doses are all unit size, then that all of these seem to look like disease type models, right? So the next thing, and we'll start this in the next lecture, is what happens if we go to D star greater than or equal to 2. So now you need 2 hits. So you can see immediately this is going to be some fun math complications, right? But you've got some memory, and your 2 hits could be anywhere in there, or you could have 3 or 4 or 5, but it's a different game, right? Now you get into interconnected, interdependent kind of things, right? Okay, so just the setup will be, we'll start with immediate recovery, if we had to do that. Unit dose sizes, it's good to keep it clear. So you're just going to have 1s in your history, 1s and 0s. And you need to have at least these D star hits in your last time steps. Okay, so we'll talk about this guy in the next cycle. I think we should move. I think that's right. Although is that lying? What's the time?
It's 5 of, so it's pretty close. It's a few minutes off.
Actually, let's talk a little more. Sorry. Evil clock. Okay. Okay. So okay. All right. Fine. So we can actually write this equation down. Okay. So the fixed point equation is going to be this. So the fraction that are infected, given that the whole thing's settled down, it's going to be so you have some. You think about one individual. It has T memory spots. It needs to have at least. Okay. So there are T choose I ways that it could have had infections. 1s in there. Right? We're going to rearrange all of those. So that's a nice thing. So it's just T choose I. We have to have all of them on. So phi star is probably that you bumped into someone who was infected. P is probably that they gave you a unit dose. So that's the power of I. And then 1 minus that to the power of T minus I. Right? So this is I 1s, T minus I 0s. Probability of doing so. And then you could have, to be infected, you want at least I has to be at least D star. So if D star is 2, you've got the sum from 2 to T. So this would be fine if D star was 0. This is a normal. This is all good. This is a fine equation. We can deal with that, or even if it was D star equals 1. But once it's 4 or 5, you've got this kind of weird truncating of a summation. All right. Yeah, and we'll always have this fixed point, p star equals 0. So that's always true. Nothing takes off. Okay, so that's fine. You can see that we'll get. Well, all right. If you put d star equals 1, then we're back into this game that you just need at least one hit, and so that should look like everything we did before. All right, so we can actually deal with this guy. So let's do an exactly solvable one, right? Because that's fun. This is really combinatorics is full of this. .NEC is full of this. You try to understand something generally, get a little solvable model out. So we can do it for some small values of t, but it's very edifying, right? General t will look like this as well. So d star equals 2 and t equals 3. So you need at least two out of your last 3 to be on. Okay, so the fixed point equation is this, right? So 3 choose 2, p squared, phi star, so this is really p phi star all squared, 1 minus p phi star. And then there's a 3 choose 1 in here, or 3 choose 3, I should say. And then all of them are on. That's what this term corresponds to. 1, 1, 1 in your history, 1, 1, 0, 1, 0, 1, 0, right? There are ways that you could have 2 out of your 3 memory, what you can remember on. Okay, your little ticker tape. Okay, new bifurcation. Yay. It's a saddle node. Okay, so here it is. You can actually, this is kind of a funny one, but you can solve it. It's got an extreme thing. So the bifurcation point is at 8/9, and the corresponding fixed point is 27/32. Because you can solve this thing. This is a quadratic, right? It's a quadratic, right? So, phi star equals 0 is a solution, and you can cancel that off. Okay, so it's a very different behavior. So up until this value of p, nothing ever takes off, right? It will, if you started with an initial infection, even all of them are on, the whole thing collapses. But if you have an infection of at least infection probability of at least 8/9, so it's a contrived example, yeah. But if it's at least 8/9, then you're in a very different behavior, right? So anything that starts here will die away. But if now it's a situation where you have to have at least a certain fraction on, and if that's on, it goes to here, right? It goes to the upper curve, which is the fixed curve, the stable point. Anything starting in here, for whatever reason, drops down to here. But this is this is now resembling of a critical mass type problem. Okay, here it's dead, but here it's a critical mass type phenomenon. You have to have a critical mass for it to take off, and we'll go boom. But there's that continuous phase transition is gone, right? That's hard to see how we could get back to that. We will. We'll actually get a very nice thing. It's to do with the integer story, actually. That's kind of, we're trying to solve it for a simple case, but the integers are actually kind of messing with us a little bit. So is that, so as soon as we went to saying we need 2 or more, right? We need something more complicated in our history. You go to these things straight away. You go to critical mass type things.
And you completely forget after 3 time steps. Go to the t equals
You
3.
forget, yeah. Your history is just marching back.
Oh, I see. So
Your window is
of those
sliding
3
through.
time steps, you need to get hit twice.
Mhm.
So okay, that's why it needs to be the infection probability has to be so high.
Yeah.
You always need 2 or 3. At
Yep.
least merge.
Yeah. So, and the recovery rate is 1 as well, right? So you recover, you escape quickly. So we'll see what happens as you dial that recovery rate. Some more fun math involved with that. But that can be the next lecture. But so all right, 2 universality classes. Interesting. And they are redolent of biological in the first case, and it's what we think of social threshold type. Yeah, but some diseases might be like this too. But you don't have to, all right, so it's over here. But the point is that it is this shape. It is a saddle node bifurcation. The real world could have all sorts of things. But this is the characteristic thing. One little model we could talk. So we'll look at some others, and we'll start to vary the dose threshold and see what happens with that in the next lecture. Okay, generalized contagion. Awesome. All right, people. Thank you for watching.
So we're moving now.